Amazing. So, how do I want to do this? You're there, you're there. Fab. Right, so starting with lecture 1, we're going to be talking about vectors. So today is really setting the groundwork of the tools and building blocks that we're going to use for the rest of the series in linear algebra. Mostly, actually, we're going to be doing a lot of matrix work, and I think matrices are best described when considered as extensions of vectors. But having a good understanding of where we're going will be important. So start off with a definition. So a vector is a thing, is a quantity that has both a magnitude and direction. So I say quantity, thing, object, mathematical terminology, but essentially it is something that has both a magnitude, so a size, and a direction. And we normally denote them either as, say, example with an underline. So if we're using sort of mathematical notation, the variables might be underlined, they might be sort of bold fonted, they might have little arrows on top of them, but that's sort of the mathematical terminology. That's the notation that we use to be like, this thing, this V is a vector. You haven't seen the underline before, so the one that I am actually going to be using the most is that one, which may or may not get complicated down the line. Equally, I think when they're sort of first introduced, the way that we sort of think about them is as an arrow, and you sort of measure the size of the arrow by the length of it. So that arrow, or that vector, has a bigger magnitude than that vector. And then it obviously has an orientation as well, like the direction is the direction of the arrow. Close enough. And then finally, you might also see them as lists of numbers. So examples of that will be, if I write a list, I can do vertical vectors, and they're called column vectors and row vectors. But like, say, 1, 2, we might do 3, 7, -1. And the style of bracket, I think, does matter depending on what notation you prefer. But so variable notation, arrow notation, or list of numbers. That will mean something in a minute. But they're all sort of interchangeable. It's just depending on what notation you prefer using. And I've seen this described as the mathematicians, the physicists, and the engineers' preference. I don't know which one's which necessarily, but they are all sort of ways of denoting them. And I think actually they're really nice ways to interpret them. Sometimes you want to think about sort of the elements of a vector, so those individual numbers in the lists. Sometimes you want to think of it in terms of geometry and in terms of arrows and shapes, and that can be the most intuitive way. And sometimes you just need it to be something inside of an equation, and that's where the variable notation can really come in handy. So each of these representations is also a way of interpreting vectors. So the arrow one in particular is a nice place to start. So arrow notation, for example, to start understanding vectors. So if we have 2 points in space, and we call them A and B. So say these are our 2 points. Then the vector V, what do I want to say here? So the vector B can be essentially the vector that goes from A to B. And we can write that as from A to B, and then this is where I would typically use the little arrow above notation. And this then gives us, it's an oriented line segment definition, because you're moving along this line. The distance between your start and your end point is the magnitude, is the size, and the direction is whatever angle you need to turn from A to get to B. An oriented line segment. So equally, we could have BA, which would then be the other way around. So going from B to A. So we can do some more formal definitions in a minute, but just for the start, we have this equation. So going, because the magnitude is the same, the negative of the vector is like the undoing of it, basically. If you go from A to B, you can go from B to A. So this is what's called a distance vector, or it can be considered a distance vector. So most vectors are actually defined from some point to another point, and the point in space is normally starting at the origin. So and these are called position vectors. So here I'm saying the origin, and what I mean by that is the vector defined as 0, 0, 0 in space, or 0 vector. And if we think about how we consider space, we typically will have some axes, say some distance in x and some distance in y, and we have a random point in space, call it P, and at the center of that our axis is 0. Then the position vector of P is, don't know why that happened. Our position vector P is precisely from the origin to the point P. And that's the position vector of P. And then its size will be its like straight line distance. If I put a ruler along that vector and measured it along, that would be its magnitude. And then we have some definition of angle as rotation round from an axis, but we won't need to worry about that just yet. Bore da, Starman, Sister T, how's it going? We are learning about vectors. Okay. Let's do another definition. So the magnitude of a vector V is denoted like this, where those straight line modulus operator there we go. I like the terrible jokes. They're the best kind. Yeah, so those straight line things are modulus or norm symbols, but we use this notation. So anytime you have a vector, to find the size of it, you do these straight lines. And this mathematically is a way of... so the formal definition is that you can compute the Euclidean norm, which is the straight line distance, which means so this is computed Euclidean norm, which is essentially just the straight line distance start and end points. Oh my gosh, she's doing the maths. I know. Which for a vector, let's do it here. So if we have a vector v where its elements, I'm going to write it in that list of numbers one again, but I'm going to do v1 as the first element in this vector, v2, don't know how long this vector is, all the way to some vn. So this is my my variable notation, my list notation, and I can draw it as an arrow as well in some space. All of these things are describing the same thing. Then the norm of my vector, the length of my vector, is computed as the sum okay. So what I've written here is the sum over all of the elements squared. So that is the same as, and then square rooting it. So the square root of v1 squared plus v2 squared plus all the way up to vn squared. And in this arrow notation, it's taking a ruler to this distance. So measure this distance in some appropriate space. So we can do a nice example. When I made an image, a vector, it's a bunch of straight lines with magnitude inventions. Okay, so a vector image is sort of a different thing, but also sort of yes. So what is it? An image vector would be each point is described by, so like RGB, for example, is a great vector, because it's like your size in red, your size in green, and your size in blue. And if you had axes that were red, green, blue, it would be describing a point in space, which I think is really, really cool, and I will geek out about at the end of this. But going back to this for a second. So our example, consider the vector v as 3, 2. So this is in our nice normal xy plane, which mathematically we call R2. R being the set of real numbers and the square because there's 2 different directions that we can go in. Then this is given like here. Yeah, vector graphics. So each pixel in a vector graph, or each... No, that's image analysis. Not quite sure, but basically there will be a vector containing the descriptions of all of the things. But it's different to a raster image, I know that much. I think it's actually that all of the stuff inside of it can be described by equations. I'll do my homework and get back to you on the vector graphic stuff. But magnitude and direction, yes, where those things are defined in like not necessarily real space. Because I'm giving you an example in R2, which is a flat plane at the minute, but we could be doing linear analysis in like R10. It starts breaking a little bit when you try and visualize that. So that's our vector v. Then the norm of v is, as we say, is the square root over v1 squared plus v2 squared, which is square root of v1 is 3, so 3 squared plus 2 squared, 9 plus 4. What is that? Root 13. So the length of that vector is square root 13. Now, and I like doing this in R squared because our position vectors in R squared, are, say I've zoomed this in, right? This is V, and the way that we get it is we go across by an amount 3, and we go up by an amount 2, and our axes are perpendicular. So what we've done is we've made a right angle triangle with side lengths 3, 2, and V, or the norm of V, is the length of that side, which is basically just my way of saying it's all Pythagoras. Okay, so V squared is A squared plus B squared. Where this is A, this is B, and that's norm of V. And that works in higher dimensions, where you then start adding in more terms. So let's take another example. So example 2, vector of 4, 0, 6, minus 2, 3. Okay, because we can have negative numbers, we can have zeros, but this is now, I can't draw that. That's in R5. It no longer becomes super reasonable to try and draw it. Please don't make me. But what I can do is I can tell you that the norm of this vector is still the square root of 4 squared plus 0 squared plus 6 squared plus minus 2 squared plus 3 squared. Classic mistake here would be to do minus 2 squared rather than minus 2 all squared. But when you're adding norms, it doesn't matter if it's positive or negative. We don't really care about direction. We just care about size. So here, this is 16 plus 36 plus 4 plus 9, which is going to give us 40, 50, 65, which we could do something intelligent with, but I'm not going to. I'm just going to leave it as 65 for the minute. So yeah, this is just Pythagoras' theorem with distances along your axes, and this works because each element... Okay, this is a very, like, I'm hiding a lot behind the curtain. Please don't acknowledge the man behind the curtain. But this works because each element in the vector is orthogonal. And what I mean by that is right angles. Okay, so in going back to my R2 example, okay, I can draw a right angle triangle. And in R3, I can do another right angle triangle, and it's also orthogonal. Orthogonal means at a right angle too. I think there's probably a formal definition that I should include here. So orthogonal is essentially the same as perpendicular. I think formally orthogonal is scalar product is 0. Okay, how do we do that if we haven't defined dot product yet? This is the thing. In R2, R3, this is as right angled. We will introduce a formal definition later. Okay. Yeah, Nightmare, I agree. That's just... we get to that at the end. Okay. Back on track, I think, she says. So, the magnitude of a vector is independent of its direction, and it's and equally even is independent of where it is in space. So I said that we normally define position vectors in terms of like from the origin to a point, but if I shifted the entire thing across in space, so say I have my vector here, v, and I take v and I copy it and I plonk it there, that vector is the same because they have the same size and they have the same direction. They're not physically in the same location in space, but that doesn't matter. So, magnitude is the same, direction is the same. That's the only thing that matters. And that's all we need for two vectors to be equal. We can define them nice and formally. So two vectors are equal. Say we can't necessarily just do that tick box, we want more proof. Then we define them as equal if they form opposite sides of a parallelogram. The best word to write with fully cursive handwriting, the worst word to write any other time. So what this means is that for a vector here and here, exactly the same vector, so if we remember that parallelograms are opposite sides, same length, and opposite angles, same size. Okay, so if this is a vector v and this is a vector w, if they have the same length, then the distance between the start points and the end points is going to be the same. And here I'm using the same hatching notation to mean these two things are the same length. And we also have that this angle matches this angle, and this angle matches this angle. And in order for that to happen, the size of v has to be the same as the size of w, and v must be parallel to w. So parallel there. Then v equals w. So parallel, same direction, magnitude's the same, they make a parallelogram, they are therefore the same, which is quite nice. Yeah, my little notation this is going to mean parallel, and that is going to mean perpendicular. And you can, I'm just drawing the lines, so it's two lines in parallel and two lines in perpendicular, and then that's the nice quick way of writing it. Okay, how are we doing? Are we all keeping up? Are we all having a good time? Is everyone concentrating on cooking dinner? So to be equal, position in space is not considered. No. So they could be on top of each other and then they would be exactly the same. But the vectors don't actually have to be on top of each other in real space. Good. Yes. Okay. So next section, I want to introduce some algebra. So that's I think basically everything we need to have perfect. To have some vectors. So we define them using these notations. So they're either going to be variables. I personally use an underline, but you are welcome to use a bold font or an arrow over the head or this like half arrow little tick thing that I do. Lists of numbers, they can be in row or columns. There is a difference. It's mostly like stylistic choice, but will matter if you mix and match between the two. And geometrically thinking about them as arrows, and maybe really complicated arrows, but arrows generally, because they have size and direction, can be quite nice. You can describe them as ordered line segments, oriented line segments even, so going from one point to another. and you define the size of them using like Pythagoras, or more generally the Euclidean norm, by squaring all of its elements. So that's a point I should say. These things here are elements of V, normally denoted VI, for just like a general, any of the elements inside of it. Some nice examples. Orthogonal and perpendicular are basically the same thing for right now. And to say that two vectors are equal, they have to make this parallelogram in space. So their size must be the same, and they must be parallel to each other. So with that, let's go on to some vector algebra, which is like one word away from the title of what we're going to be doing today, for the rest of the mini-series anyway. So the way I want to go about doing vector algebra is I'm going to try, and please forgive my drawing skills, I'm going to try to introduce everything geometrically first, and then bring the maths into it afterwards. So I'm going to do my nice arrow definitions, and then I think we all know I'm an engineer at heart, and I just have to accept it, but let me have this. Yeah, so I'm going to try and introduce things geometrically and draw them out, and then we'll worry about the maths after the fact. Hopefully once we have that visual intuition. So, for any two vectors, V and W, we denote their sum, V plus W, so we can add vectors together by aligning the initial point of W with the terminal point of V. I'm writing out a load of words, then I'll draw it, don't worry. So what I mean by that is, say we have a vector here V, and we have a vector here W. Then to get V plus W, I take V, and I plonk that down, and then I take W, and I align the end of, please let me put line out, there we go. I align the end of V, so remember it's from the start to the end, that's the direction of the arrow, with the start of W. So I move as much as V tells me in the direction V tells me, and then I move as much as W in the direction W tells me. And what that then gives me is, and I'm going to use the straight line tool because otherwise I will mess it up, that vector there, which is then V plus W. So I've moved along one and then along the other. And it's worth noting that this is equivalent to doing it the other way around. So I can move along W and then move up V. And I can hopefully do this by just copying and pasting as a visual proof. If I then pull this arrow in space, it should be nearly the same. And that is because my way of drawing arrows is a bit rubbish. And this is W plus V. They're basically the same thing. There is an important distinction, but we'll get to it later. So V plus W is the same as W plus V. And you can think of it, because it's a list of directions, it doesn't matter if I walk to the left, then walk to the right, or if I walk to the right and then walk to the left, I still get back to where I'm going. There is another definition that I've seen used, which is similar, but sometimes if you prefer, there's a different geometric interpretation that I've seen that people might like. So alternatively, we set the initial points of V and W to be equal, and say that V plus W is the diagonal of the resultant, which is an incredible word, and we're back to parallelograms. There's a lot of parallelograms in vector algebra, it turns out. So let me pull these guys again. So I get my V. And I get my W. And now I set the start points to be the same. Okay. And then what I should have is my V plus W as the diagonal of the parallelogram. So I can take that line and plonk it there. This is why you should always use straight lines when doing you can see that it does pretend it finishes off a parallelogram. There you go. Exactly. So, and this gives you your two, if this direction was V plus W, and this direction was W plus V, they both get the same thing. So this just further demonstrates you can swap them and get back to the same. So, finally, mathematically, this is computed entry-wise. So what I mean by that is if V is given by its elements Vi and W is given by its elements Wi, then V plus W is the list of elements Vi plus Wi for each matching I. So V1 is added to W1, V2 is added to W2, and so on and so forth. So this is a good point, that you can only really add vectors when they are the same length. You can't add a 2D vector to a 3D vector because you're then missing, you have Vi plus something. And, well, that something is nothing, and then that breaks. So example, if V is 2, 3, 5, and W is 4, minus 1, 0, then V plus W is 2 plus 4, 3 plus minus 1, and 5 plus 0, which is 6, 2, 5. Okay, and that would be the same if I did it the other way around as well. So normally when you do algebra, you do addition, subtraction is exactly the same. You can see that when we subtracted element-wise, it's the same thing. So V minus W we need a good sense of what minus w means. And that's where we go back to our sort of position or oriented line segment definition. If the vector from point A to point B is given from one to the other, then if I take the same thing somehow and I reverse it, I get minus AB, which is the same in this case as writing BA. So the negative of a vector, so minus V, is the same as same magnitude as V, but opposite direction. Okay, the distance between my points hasn't changed, but the order I do them in is backwards. So instead of going forwards, I go backwards, that's opposite. Instead of going left, I go right. Instead of going up, I go down. And so on and so forth. This can also be thought of as minus 1 times V. Okay, so if we wanted to think of it that way, we need to understand what does it mean to multiply a number by a vector. So what does it mean to multiply a scalar by a vector? Where here I've just introduced more notation without defining it. So scalar is quantity with only magnitude. So this is just size. And that's your standard numbers. The classic side example, just a quick aside, if speed is a scalar, velocity is the corresponding vector. So a car going 30 miles an hour, 30 miles an hour is just its speed. A car going 30 miles an hour north is a velocity. And two cars both going 30 miles an hour in opposite directions have opposite velocity but the same speed. So when we're now talking about scalar quantities, we're just talking about numbers. Okay, they just have size, they don't have any direction attached to them. So scalar is the scaled down version of a vector. Matrix and matrices are the scaled up versions, which we will get to in a bit. So enough of that. So when we multiply scalars by vectors, we think of this as stretching them. Stretching slash scaling them. Scalar value won't change the direction, only the magnitude, okay? So a good example of this is if I take my vector v, I can stretch it to twice the size and have 2v. I can halve it and get 0.5v. Or I can I rotate this? I can. Go in the opposite direction and get minus v. So when you multiply by a scalar, you can stretch it and shrink it. No worries. Nice way to see this is going back to our classic R2 example, because drawing things in 2D space just is easier. If I have the vector, let's go 1, 2, then I go along 1, and I go up 2, and that's my vector. If I do 2v, then I do 2 times 1, 2. And I need to be careful here because this is not brackets as in, well, it sort of is brackets as in BODMAS, but like, I'll write it. A better way to write it would be to take it out, to take it element-wise. So 2 times 1 and 2 times 2. So you do each element individually. So this is 2vi. Okay, every element gets multiplied by 2. And what that means is, well, 2 times 1 is 2, obviously, and then 2 times 2 is 4. So I go across 2, and instead of going up 2, I go up. To there, 4, 2. And now my new vector is, it's got the same gradient, but it's just twice as long. So it's the same direction, it's just scaled. No, you're totally okay. Don't worry about it. Welcome in. So, to summarize, scalar multiplication. Stretches or even inverts direction on size and positivity of the scalar. So I gave 2 examples in positive, and then I gave one like just minus v, but we could do minus 2v, which would then take that stretch and rotate round. Or we could take something smaller than 1 and compress and rotate. If y'all remember, it's just like scaling transformations. So in, I know it's in GCSE maths, I think, when you do your different transforms on a grid, you've got like rotation, reflection, and then scaling and scale factors. And that's essentially what it's doing. It's scaling your shape or your vector by an amount, and that can be negative. So let's do some mathematical definitions on this. And this is where I like introducing Greek variables to be my scalars, and keeping Roman letters as my, do I mean Roman letters? Arabic letters? No, my alphabet as vectors. So for scalars, lambda and mu, and vectors, Latin letters? I mean Latin letters. A, B. I mean, I will try and make sure that I underline everything that is a vector. I am sometimes bad at it, but vectors AB, scalars lambda mu. We have the definition. So lambda times mu A is the same as lambda mu A. Lambda plus mu A is the same as lambda A. So this is where BODMAS starts coming back into things. Latin alphabet, Arabic numbers, thank you. That's what I mean. Lambda A plus B is the same as lambda A plus lambda B. BODMAS, PEMDAS, PEDMAS, whichever variation, I think like BIDMAS, whichever one of those you want to go with, it's that. So for example, if lambda is 2 and mu was 3, this would be saying that 2 3a's is the same as 2 times 3a, which is the 6a. Here you've got 2 plus 3a is 2a, 2 lots of a plus 3 lots of a, which is still 5a. And then here 2a plus b is 2a plus 2b. Okay? So that's that's basically just saying that your scalar vector multiplication can behave the way that you would sort of expect it to. Another definition that I sort of rolled over earlier that I didn't go in full heavy on, that we probably should, is our zero vector. So zero vector, and here I am writing, that's a 0, not an O, has length 0, and no / every direction. This is ill-defined. And basically, direction, whichever is useful. Realistically. And this zero vector is 0i, like every element is 0, basically. It's 0, 0, 0, 0, and so on and so forth until for the appropriate amount of zeros that you want. And it is typically used as the position vector of the origin. Origin being center of your axes. So for, say, xy, we write 0 there. That's our origin. But this is useful to know because we need well-defined algebraic terms, because we're going to finally do vector arithmetic. And this is for vector-vector addition. So remember before that we had v plus u is u plus v. So when we add two vectors together, it doesn't matter what order we add them in. This is called the commutative property. Okay. If we added the zero vector to a vector, it doesn't change its length and it doesn't alter its direction. So v plus 0 is the same as 0 plus v because it's still commutative, and it's just the same as v. So we can add 0 to something and it won't change it. And this is what's called the additive identity. So, or 0 is the additive identity. So in maths, when we say identity, we mean like the thing that we can do that won't change anything. It's the function that maps something to itself. Or essentially like the world's most useless thing, but it's good to know that we can do it. Like there is something that takes a vector, a function, a variable to itself. This is the same in normal arithmetic. If you add 0 to something, it doesn't change the value. Anything plus 0 is 0. So 0 is the additive identity. What else do we have? We have u plus v plus w is the same as u plus v plus w, which is another way of saying it's order invariant. It doesn't matter what order we add our vectors together. You're still going to get the same thing. And mathematically, this is the associative property. And then finally, we need something. If we have v plus 0 is v, there must be something that we can do that maps anything to the 0 vector, and that's the inverse. So how do we undo a vector? And what I said before is, well, you go, if I go left an amount and then I go right the same amount, I get back to where I started. If we take a vector and we add its opposite to it, so opposite direction, same size, we get back to 0. And this is called the additive inverse. So the inverse of a function is something that undoes that function. The inverse of a vector is the one that is opposite of it. And basically, mathematically, that means if I take the thing and I take its additive inverse, I get 0. So those are our rules about adding vectors together. Okay. It's a nice little list of some vector identities for you. And these things are always true for any vectors v, u, w. Okay. We're going to take a really quick break. Hello. We're going to take a really quick break and then we will get back in. I am about... Oh, I'm quite close to the end of where I wanted to get by today. I'm quite happy. We're doing all right. So, upcoming next, we are going to introduce unit vectors because that is the next obvious step. We're going to introduce a nice basis for those of you that know where I'm going with this. I want to build up describing vectors in terms of the directional unit vectors in Cartesian. I'm going to quickly introduce the projection of vectors because that's going to be useful down the line. And then we're going to introduce the dot product, which will leave us with it will set us up nicely for next lecture where we start going into linear transforms and matrices in terms of linear transforms. So yeah, that's where we'll get back to. We will be back in about 5 minutes, if not slightly less. So I will see everyone soon. Hello, we're back. Right, where am I going? Let's give it a second, get everyone back in, and then we'll keep going. Yeah, I think this lecture is like a lot of definitions being thrown at you. I'm hoping that future ones will have more examples at the very least. And as I say, there are some really cool like real world applications of this stuff. The one that I'm sort of geeking out about the most at the minute is the fact that, as I was saying, like RGB, I've always been aware that it's essentially a vector where each entry is like the quantity of how much red, green, and blue you have. And that's where you get like RGB definitions either like out of 255 if you think of them as like measures of how much, or like their percentage or decimal fractions of like 0. It's out of 1, where 1 is like the most red, so 111,000. Those two values correspond to like black and white, so your RGB all on full is white light, 000 is black, it's no light. But that's how you define vectors, and you can define colors, and it's in like 3D space. And I always get really geeky whenever I see on TikTok people have those like color grid, like color cubes, or the like hairdressers will be talking about how you take hair from like this color to that color, and you have to like go through these spaces of color, and they have these wheels that have different gradients, and you move through this color space. Normalized color specs, yeah. That's all vectors. That's all maths, and that's really fun. I like that. As someone that dyes the hair a lot and asks insane, can I go green? Realizing that the color space and additive color theory is like actually just linear algebra. 10 out of 10. Absolute 10 out of 10. And I think it's an example from next lecture. We're going to talk about doing math with color, and that'll be really entertaining. And I might even do it using the light, because I have now figured out, I don't know if I can, that's not going to reach. With the Stream Deck, I've now got the colors changing. So we'll be able to get all of that playing around as well, and be like, right, if you add this light to that light. Yeah, because it's I said the current thing that I'm obsessing over, and this is like the 3rd time. Leave me be. I just think it's really cool. Anyway, let's get back into what we're supposed to be doing today, which is vectors. So, coming back over here. Hello, welcome in. Sorry, I love your username. 10 out of 10. Right. Where were we? So that concludes, for now, vector addition and vector scalar multiplication. And I say for now because we're going to come back to it. But within vector scalar multiplication, actually that doesn't conclude it, because I'm literally about to talk about it again. Sorry. Okay. The final thing in scalar vector multiplication is defining our what are called unit vectors. So if we can take any vector v that has a direction and we can multiply it by any scalar number, what that's going to do is that's going to create a family of vectors that are stretched and compressed along that direction, right? And they're all going to be pointing in the same direction, but they're all going to have different magnitudes. So perhaps instead of thinking of a random vector as the size and direction, we think of it as a stretching of a base vector. So the base vector, the unit vector, gives us our direction, and the scalar corresponding to that gives us our stretch. So instead of considering, can we do a quick scale over the board? Yes. And that gives me time to think of how I want to phrase the next sentence. So, brief summary of where we've been. Vectors can be defined, can be written down in one of three ways. There's probably more, but these are the ones I use. Either variable notation, so denoting them V with hats or boldface. I do underlines for my vector notation. They can be drawn as arrows, or they can be considered lists of numbers. But vector is a quantity that has both size and direction. Okay, so it not only is how big it is, but what direction is it pointing in. The iconic one is velocity, is speed plus direction. You can think of it as an oriented line segment. So between 2 points from A to B, a vector describes it, and that's the distance between the points and what orientation, what direction it is. Equally then, you have another vector going in the opposite direction, so from B to A, which is the negative of it, or the additive inverse of it. We describe the size of it as the length of it, which we showed in R2 is the same as taking Pythagoras, because your vector in 2D, you go sort of along your x-axis and up your y-axis, and that gets you to your point, but that's the same as doing Pythagoras to get the Euclidean norm. So squaring the sides and then adding them and square rooting the whole thing will give you the length of your vector. At the minute, our scalars are exclusively real numbers. We'll stay in that world for a minute. Everything's Pythagoras, even in higher dimensions. You do the same thing, and it's Euclidean norms, but it's still basically Pythagoras for now. We introduced brief notation to orthogonality, which we're going to get onto again in a minute. But that's basically saying everything's at right angles to each other or perpendicular to each other. We said that vectors are the same, either if they have the same size and direction, or formally they are equal if they form the opposite sides of parallelogram, which is a shape where opposite sides are the same length and opposite angles are the same size. And that is just another way of saying same size, same direction, they are this equal vectors. I introduced my notation for parallel and perpendicular. And then we did some vector algebra, which is basically saying the way that we add vectors together is by going along one and then going along the other. And we can do that reflexively. So we can do v plus w, but we can also do w plus v. Equally, we can set the points, the start points of the two vectors the same, and then it's the diagonal of the corresponding parallelogram. We love a good parallelogram in vector algebra. But again, it's you go along v and then you go across w, and that will get you v plus w. Mathematically, this is done element-wise, so for each element so you take the first number in V and the first number in W and you add them together, same with the second, same with the third. And this is what showed us that we need vectors of the same length. So you can't add a 2D vector and a 3D vector, things must be the same magnitude. Then we started talking about what it means to multiply a vector by a scalar, and that is basically the same as scratching. So you're applying a scale factor to them, and that's sort of where we were going to with this. So we did some nice quick definitions of the mathematical rules that were allowed for multiplying vectors together, multiplying vectors by scalars, introduced a zero vector, and then we did some nice arithmetic rules, including additive inverse, is something that's going to come up a lot, where you apply a vector, apply the opposite vector, you get back to where you started. You've moved 0. And also the identity, where if you add 0 to something, you get the same thing back. So v plus 0 is just v. And that's where we were. So, as I was saying, if we have a vector v, but we also have vector 2v, and we also have vector 0.5, 0.3v, and so on and so on. We have all of these vectors, but they all have direction. Then what we can say is that they are all equivalently some scalar value lambda times v hat. Now this is where you'll learn why I do my underlining, and it's because I regularly have to introduce things with hats. Where for their own lambda. So each of those has a unique lambda, and what that means is there's a different scalar multiplied in front of it. So for their own value of lambda, and v hat is the unit vector in the direction of v. How long is this stream? I have a page and a half left on my notes. I have no idea what time it is. Thanks. Okay, so let's do the definition. That should probably be fine. Thank you. Oh, fab. Yeah, that should be all right. For a vector v, v hat in and then we write this out as v hat is the vector v divided by the norm of v. Don't change notation on you too quickly. Where that's the magnitude of v. So basically, i.e., it's the vector with the same direction as v, but length 1. What is going on? So if this is v, then the unit vector v hat has length 1 in whatever in whatever scales you're using. So in R2, any vector of length 1 is going to be sort of, you know, there or anywhere in this circle. Okay, all of these have length 1. I don't see anything. I got it. There we go. Okay. Now this is going to come in really useful. remember, we describe vectors as lists of numbers. So this is basically where linking vectors to coordinates is going to be really useful. So you may have first been introduced to vectors, again, through that position vector definition, as it's a set of coordinates. Okay. Also remember that we can describe vectors as sums of other vectors. So remember, v plus w is v plus w. Then if I come back to my nice classic three-dimensional space, that was an aggressively big arrow, that was unnecessary. So I'm now in R3 and I do x, y, z. Then what I can do is, and this is what we do, I can define a unit vector in each of my three directions along three of my axes. So I have vectors of length 1 that point in each of my three directions, and each of those directions are at right angles to each other. Remember, they're perpendicular. And I'm going to define them as I, j, and k. Where I have, so remember they're lists of vectors, they're lists of entries. I is, I go distance 1 in the x direction, 0 in the y direction, and 0 in the z direction. J is the same, but now in the y direction. And k is the same in the z direction. Okay, then I can write any vector v as some scaling of these, right? Like when you define a position in space, you go some amount along your x-axis, some amount along your y-axis, and some amount along your z-axis. That amount is the scalar that you multiply it through I, j, and k through by. So if I was going 2 along in the x direction, I would do 2i. And I can then define v as some scalar, okay, we're going to do it this way because this is the nice way. AI plus bj plus ck, where a, b, and c are scalar. A, b, c, scalars, and I, j, k are my unit vectors. And then this gives v as a, b, c. Children. And then there's some nice projection down onto each of these directions that we need to do. Mu, v, and tau, and lambda. Yeah, I thought about it. I decided against it. Where we've gone like along each axis in that amount to get there. So this is the standard definition of vectors and coordinates in 3D space. So this, when we define it this way, we are using what are called Cartesian coordinates. There are other coordinate systems and other like descriptions of base vectors which has directions x, y, z, and we're going to go on to what it means later, but basis vectors I, j, k. And I, j, k and x, y, z, like, I'm not picking I, j, k randomly. These are the ones that are used in the literature. Is it possible for me to upload this over on YouTube? Yes, definitely. Our old mechanics mini lecture series is on there as well. It might be just the raw upload from the VOD, but I might also try and chop it down into something coherent. If I don't chop it down, hello future. But yeah, it'll be on there hopefully within a week. That's my goal to myself, is to try and upload them within the week, to give time for before the next one. But yeah, so that's that for the minute. Final things that we want to touch. No worries at all. It is currently the only long form content I have. If you don't include videos I've done with Simon. No, I, j, k are all orthogonal to each other. Okay, so if I just looked at I and j, they would be at right angles. If I looked at j and k, they would be at right angles. And if I look at the other two combination that I forgot about, they're all right angles. And that's where you get your nice right angled coordinate system from. Let's do a random tangent. Because I can't link this nicely. Hi, Icarus. I'm trying to get back into evening streaming. What of it? So we say that A is the... Oh no, wait, that it does relate. Haha, I win. Okay. Pretend I didn't say that. Those watching back the VOD, you'll never know. Okay. So we take our vector v as ABC. Okay. You want a random tangent. I'm sorry. I linked it together too well. I linked it together so well that even I didn't realize. Take the vector ABC with A, B, C in R, so they're just all real numbers. I'm so smart, I tricked myself. That's what happened there. We say that A is the projection of V onto I. Okay, so what that means is, i.e., A is the amount of V that is parallel to I. So when I defined V, I said we go, the amount A along in the I direction, the amount B along in the J direction, and the amount C along in the K direction, or in the X, Y, Z. So we constructed V, we made V from this nice ABC definition. But we can do this in any direction. So this can be generalized. So if I take two vectors, v and I take n, say, then I can work out the projection of v onto n. So the amount that v goes in the direction of n is the amount that it's perpendicular. So this vector here is what's called the projection in the direction of n of v. And then the opposite of that, so the bit that's left over, is called the oproj, so the opposite projection. These definitions are a bit gross, but the thing to note is that for any direction n, we can do this. And the vector v is the sum of those two vectors. And this is true for any n. I think that's for any n not equal to the 0 vector. Because the 0 vector doesn't have a direction. So I think that breaks it. Now, that's not necessarily the most helpful for just a generic vector, but it is useful if you want to work out, say, for a given vector in x, y, z, you want to work out, say, the amount that is vertical of this random vector. Or if we're in a different coordinate system and we don't have it nicely defined as this sum over ijk, or we need to find it in a different vector, or we want to find how aligned two vectors are, that is a really useful way to do it. Now, we'll get on to how you actually compute that later. So, I guess the projection on the 0 vector would be 0 and the opposite is just v. Yeah? Left as an exercise to the reader. Anyone watching a VOD back, put it on the YouTube comments or DM, or don't DM me, I don't respond. Put it in the YouTube comments. That can only end well. Okay. I'm so professional. I think this is how you know I'm a real doctor of maths, is because I'm like, what if it's just an exercise for the reader, you know? What if? Okay. The final thing today. We've done vector-vector addition. We've done vector-scalar multiplication. What about vector-vector multiplication? Well, it doesn't really exist, except it kind of does. So, multiplication isn't quite the right thing. Terminology to use anymore. We have a few vector-vector operators, but the nicest is what's ironically called scalar product. So weirdly, the vector-vector multiplication, and I use that term really loosely, is what's called the scalar product, which feels ironic, but we'll go with it. So you can define that element-wise, but it doesn't always makes sense. So like you can do that in like MATLAB and in coding. Yeah, but it's more used in terms of like yeah, I can't think of an actual example of why you would need that. All vectors projected onto the zero vector form the vector null space. There we go. Okay, I knew people in chat would know what's going on. Okay, let's do my definitions. The scalar, also called the dot product, which in my opinion is a much more fun word for it. Because why give something a complicated name when you could just describe it as the symbol you use? Between two vectors, A and B, is a measure of how perpendicular the two vectors are to each other. It's named the result, scalar, or the symbol dot. Okay? And what I mean by that is the output of the scalar product is a scalar. So you take a vector, you take another vector, you get a scalar out of it. So I'm going to write a load of maths and then I'm going to outline what is going on. So this is the dot product, A dot B, and that is equal to the sum over the product of the entries, but it's also equal to the product of the norms multiplied by cos of theta, where we have, okay, this is our dot product. This is the sum over these. So that's A1, B1 plus A2, B2 plus so on and so forth. These are our vector norms. Cosine function, angle between the vectors. So if this is the vector A and this is the vector B, this would be theta. Why are these formulas equals? So these are two different ways of computing the same thing. And you can sort of back engineer them. If you, I don't know what the proof of that is. Let's find out. Ah! I knew there was a reason I did projections. So if I take my two vectors, oh, I didn't underline. Bad. Then this distance here is A cos B, cos theta, right? Because it's didn't know we do lectures here. We do sometimes, yeah. I think it's something around this. So you take the projection of one into the other, and you get that the angle between them is something like, and this is going to be like, angle gives you the distance. Yeah, so you can take it as a triangle. This is theta. This has side length A. That has side length A cos theta in the direction of B, which is parallel. What does that have to do with the sum of AI, BI? That is to do with, good question. I'm assuming something to do with the fact that you get, so you get that. I am working this out on the fly, by the way. So then that's going to give you, like, so that, that's not just going to be the direct, like, you don't then get AB, basically. They never showed the proof at A level. Both products are a thing that pop out of the quaternions. Oh, okay. I tell you what, I'm going to go look at it. We'll get back to you next lecture, because I cannot do this in my head right now. But there will be something that will get us back to where that is. Place A with A over mod A and assume A equals B equals 1. As soon as you assume that they're equal to 1, then it's not the same, right? Okay. Homework for Cat. Okay. The main thing to take away from this is that when I say it's a measure of how perpendicular they are, we can think of it in terms of cos theta. So if we know that our cos theta does this sort of behavior, okay, where we have 2 pi, 0. And here I'm defining in terms of radians. Which are between 0 and 2 pi, not degrees, which is 0 to 360. I will probably be sticking to radians throughout this series, so things to know. 2 pi is 360 degrees, pi is 180, and pi over 2 is 90 degrees. I'm going to put arrows just so people don't come at me for writing equal signs. Essentially what you have is that this tells you that A dot B is equals to 0 when A is perpendicular to B, and A dot B is largest when A is parallel or anti-parallel to B. So when they're aligned to each other, you're at 1 or minus 1. So here and here, A is parallel to B, or anti-parallel. And when you are here and here, A is perpendicular to B. Okay? So that gives it's a measure of how aligned they are. So the biggest value you're going to get, where you just multiply the vector norms together, is when they are parallel, and you just have the dot product is the same thing as multiplying their sizes together. So let's do an example. If we have A is, I'm going to go back to my old vectors, so 2 and 3, and B was, what was it, 4, 1? What did I use as the... Yeah, 4, 1. Okay, then A dot B is 2 times 4 plus 3 times 1. So sum over the products of the entries. So we get 8 plus 3, which is 11. Now, equally, we could try and work out the norms of them. So we get the norm of A is the square root of 2 squared plus 3 squared, and the square root of B is the square root of 4 squared plus 1 squared. So that's 4 plus 9, so that's the square root of 11. And that's the square root of 17. Wait, 13 even. 9, 10, 11, 12, 13, yeah. Then we need to work out the angle between them. So we would do something, which I have forgotten. Okay, and then okay. So that's not how you work out the angle between vectors. Yeah, we can work it backwards to compute it. I was trying to go both ways in, but what we could do is A dot B equals mod A mod B cos theta. So we get 11 is root 13 times by root 17 cos theta. So cos theta is 11 over 13 times 17. Arc cos. I like doing cos in -1. I'm not responding to that. And you can work it out that way. There is another way that you can work out the angle between the vectors, but I have completely forgotten it. So only thing left is some dot product rules. And that is, so two vectors, a vector dot producted with itself is obviously in the same direction, so cos is equal to 1, and then you just do the norms times the norm, so that's the norm squared. Similarly with our vector addition, because it's a measure of angle, it's going to be the internal angle between the two vectors, so A dot B is the same as B dot A. we have for scalar value lambda, a dot b is the same as lambda a dot b. Remember, it's a measure of angle, so multiplying by a scalar doesn't matter too much, but what you don't do is take that inside. It's not distributive across the dot product. It's not lambda a dot lambda b. A dot, and then we can do b plus c. This now is distributive, and you get a dot b equals plus a dot c. So the dot product is distributive over the plus, but not the other way. Okay, in summary, we have done a fair chunk today. So these are basically all of the tools that we're going to be using throughout when we start talking about vectors. We are obviously going to move on to transforms and linear maps, but this is sort of the building blocks that we're going to be using. So things to remember: vectors are both magnitude or size, and a direction with a list of numbers, an arrow definition for geometric or variable notation. I personally use an underline under a vector variable. So that is going to be, if you see an underline, it's a vector. If you don't see an underline, hopefully it's not a vector, or I have made a mistake. You can think of it as ordered line segments, so that's why maybe we do that arrow above the top from point A to point B. And we can think of position vectors as from the point 0 to the point P, and that gives us our position vector P. But we don't need to be specific in our location in space. We can move around space. The length of that vector then or the magnitude is denoted with these modulus signs, so the straight lines either side of it. And sometimes I call it the norm because you compute it using the Euclidean norm. So you take all of the elements, you square all of the elements individually, add them up, and then square root it. And that is the same as doing Pythagoras in 2 dimensions. So Pythagoras' theorem, you sum the squares of the opposite sides of the vector. And you do that, but just in more higher dimensions. So we can do it in any dimensional vectors. We introduced the definition of perpendicular because I jumped ahead. And we said that magnitude, or vectors being equal, is independent of their position in space. And 2 vectors are considered to be equal if they construct opposite sides of a parallelogram. We then did some vector algebra. So to find the sum of 2 vectors, you sort of do them top to tail, and you do one then the other. Or you can say that the sum of them is the resultant diagonal of the parallelogram spanned by the 2 vectors. So take the parallelogram where 2 of the sides, or 2 of the adjacent sides, are the 2 vectors. It's the diagonal across. So the 2 different nice geometrical definitions for that. Mathematically, it's summing the elements individually. We introduced scalar multiplication across vectors. So that's considered the same as doing sort of scalar transforms of coordinate spaces. So you're stretching, compressing, or sometimes inverting, going in the opposite direction. If you multiply by a negative number, you can stretch in the negative direction to sort of undo it. And that's the equivalent of what you do when you multiply through by a scalar. We introduced some rules. So there's a lot of rules for vector algebra to think about, whether you've got vectors, scalars, and you're doing multiplication or addition. Zero vector, just defined as the 0. More arithmetic rules. Now we have introduced terminology like associative, commutative. There is a rule that's transitive somewhere that I've forgotten, but we've also introduced the additive identity and additive inverse, because we're going to be seeing a lot of identity functions and inverse functions. Identity function being, I apply this function, I add 0 in this case, and I get the same thing back. It doesn't do anything to what I have. The inverse then is I am undoing the thing that I have. So u plus the minus u gets you 0. We introduce unit vectors, which just have length 1, and you can find the unit vector in the direction of a given vector by dividing by its size. And you think of it, you're scale factoring, you're shrinking it by the amount that it is, or you're scaling it up by the amount that it is, the opposite of the amount that it is. We introduce the unit vectors in each of the 3 cardinal directions. So in Cartesian coordinates, we define our vectors as sums over ijk, which ijk each point along each of the 3 axes. In 2 dimensions, where x and y, we just have I and j. And this is where we really get back into that coordinate system thinking of vectors. We briefly introduce projections of vectors. So we say the amount a vector is pointing in a given direction for another vector. And that's where this ijk comes in. A is the projection of v on I in this definition that we have of v as ABC here. That's really useful as well when we think about dot products. So the dot product is the measure of the distance of the angle between 2 points, the angle between two vectors. And it's done, either the dot product or the scalar product is computed either by summing the products of the elements, or taking this equation where you multiply the norms by the angle between the two vectors. And this is normally used to describe, as I say, the measure between the two angles. It is biggest when they are parallel and smallest when they are perpendicular. It's actually 0 when they are perpendicular. So we can figure out if any two vectors are perpendicular to each other because their dot product will be 0. We then broke my brain a bit about why this was a proof and why this works. I've forgotten, we'll do that next time. And then we finally introduced some dot product rules. Ugh. We did it!